If not, you can always rip the recording from wherever it's possible. Okay, all set up, all running seamlessly. This is what we like. So I would say it's a delight to be here, but I'm here every day of the week. So thank you for coming to Holloway, and thank you for seeing our state-of-the-art lecture theatre with wonderful shades on, so the undergraduates can repose during our lectures. So I was going to introduce myself. It's already been done, but fundamentally I'm a geophysicist who is interested in geohazards and water. So it's a bit ironic that I'm speaking to the Thames Valley Regional Group, and what I could more relevantly perhaps talk about is the chalk, which I'm very into, London clay, which I'm into, and the oolites of the Cotswolds, which I'm also very into from a geohazard point of view. However, we're not going to do that today. We are going to speak about a relatively new topic to perhaps some of you called citizen science. So the overview of the talk, I haven't timed myself. Should probably take a roughly 45 minutes to an hour. First of all, we're going to go through some preliminaries, as I normally do for undergraduates. So introduce things like what is citizen science, and try and do it in a way that is as exciting and not dry at all as possible. Then what we will do is we will take a detour into technological innovations like low-cost sensors and smartphone apps, and we can see how these marry seamlessly with the principles of kind of participatory citizen sciencey monitoring techniques. Then the bread and butter, the meat of the talk, will be a case study of my work in Nepal, which is aimed at boosting resilience to floods and droughts and landslides using citizen science techniques, before taking a step back to England and looking at how we can use these techniques at the top of the Thames Valley in the Cotswolds, the Thames Head, and the bottom of the Thames Valley, so around here, Egham, London. And also, we will take a slight detour via Madagascar as well. So at the very end of the talk, we're going to be having our fingers in lots of different pies, and we're going to be visiting lots of different locations. So to start off with, what is this thing? So I'm going to shoot myself in the foot immediately by saying I really don't like the term citizen science. I don't think it's very often that a speaker kind of rubbishes the title of their talk so early in the talk. But citizen science, and in a talk like this, you will end up saying the word so many times it gets stuck in your mouth, is essentially the involvement of non-scientists in scientific research projects. It's as simple as that. There are a million and one different definitions depending upon who you speak to, but that is the intrinsic definition. That's all that you need to know. Members of the public involved in funded scientific research. I don't like it because I think it gets overused. I think it reached its peak sex appeal, as it were, in terms of funding in about 2015, and I think it's overused. I also think it is a particular thing, a particular discipline, which is very easy to do badly and very difficult to do well. So in that sense, it's very similar to geomorphology. Lots of kind of handle-turning geomorphological papers on hill slope processes and river meanders, etc., etc. But there are very few really cutting-edge ones. So there are lots of different words for citizen science. This is the boring part. So citizen science, community engagement, participatory monitoring, they all essentially mean the same thing. And here's a typology which we developed 5 years ago of different levels of citizen science from 1 to 4. So the numbers depend upon how involved the non-scientists are in your research. So you might be involved in a project, a citizen science project, but you might not know that it was a citizen science project. So for instance, counting the number of birds in your garden and reporting it to the RSPB or something, or looking up at the stars and saying, can you see Orion this evening, or is the light pollution too bad? And then reporting it to a university or something like that. So that is the most basic form of citizen science, where you, the person, is acting as a censor. You're not really involved in the research, you're just being used as a kind of tool, as it were, to collect data. So what I'm most interested in is if you climb the levels and you get up to the 4th level, there is a form of citizen science known as extreme citizen science. I didn't coin the word extreme. This was done by a Dutch lexicographer in 2014. And this refers to the intrinsic involvement of non-scientists right from the problem conception, data collection, data analysis, and then the dissemination of information which has been processed by us, the scientists. So I think that this extreme, maybe we won't refer to it as extreme, but maybe total involvement, citizen science yields the greatest impact in terms of science and in terms of, yes.
I just have a quick question on the Zoom. The slides aren't moving for them. Just wondering if there's something we could do about that. You might need to come in and out.
Does it work if I do it in this view?
That seems to work.
So if the people in the audience can put up with having a bar down here and a bar up here, I think we'll do it that way. There's sometimes an issue on Zoom with the full screen mode on PowerPoint. Who knows why? So yes, any research project, any physical science research project, I think can be divided up into data collection, data processing, and then data feedback, information dissemination stages. So this kind of tripartite structure. And I've indicated just below here the ways in which involving non-scientists can be beneficial in each of these stages. So getting information from sensors brings in new technologies, which we'll discuss in a minute. Processing the information takes advantage of the internet and the Internet of Things, which refers to the fact that there's all manner of gadgets and wearables and things which exploit the internet. It's not just a smartphone and it's not just your computer. So all sorts of devices which use the internet. And then finally, the provision of information. And this is where social media, smartphones, and gadgets come in handy. So there's all sorts of ways in which the principles of citizen science can fit into a research project according to this tripartite structure. Okay. So at the most elaborate version, this is some of the most advanced work that stemmed from one of my citizen sciencey research projects. And this is a decision support system, which we developed to be used on a smartphone. And this is developed for farmers in Nepal and farmers in India. And the idea is that they get multiple streams of information coming into them, weather data, water data, hazard data, and then they can do some on-the-fly processing to see where the most efficient places to grow their crops would be, what kind of crops they should grow, and they could look at current market prices to work out how much their yields should expect to sell at. So this arose from the needs, the community livelihood needs of the farmers, which we solicited. They wanted something like this. We tested it with them. We did user-driven design with them. This was what they wanted, and it's helped them to improve their harvest. So this is really, the scientist and the non-scientist as equals, as opposed to us flying in as kind of Western scientists from Britain and telling people what to do in a very bossy way. So this is one of the most kind of successful, an outcome of one of the most successful projects that I have worked on. Okay, so the final wordy slide. These are some of the most important issues when you are planning a research project that involves non-scientists. So first of all, you need to work out why would people want to work with you. That's an issue of motivation. And what can be done to incentivize people to work with you. And sometimes this just involves giving them money. So I've written at the top, there are 2 bullet points which use the word intersection, and I've highlighted that one of those intersections in this kind of Venn diagram down here. So before undertaking a research project, you need to try and identify a shared space between supply, so what we can offer as scientists, and demand, so what the non-scientists want out of the research. And if you can kind of get a mutually beneficial shared space here, this is where you want to be aiming at. So people on the ground will want you to solve every tiny issue in their lives, and we can't do that as scientists. And likewise, some of the issues which are presented yield no scientific insight, no scientific relevance, not relevant to earth sciences whatsoever. So you have to work out what can we do versus what do people want. You have to realize that we're not a charity, nor are we a consultant. So the work has to be scientifically impactful. So it has to advance fundamental process understanding, and it has to yield some form of impact on the ground, be that improving people's livelihoods or reducing their risk to landslides, geohazards, or boosting their resilience. So incentivization and motivation are very important. And as well, one has to think about what the effect of coming into a community with big scientific ideas and telling people sometimes things which they don't want to hear, what that's going to do to the community and their fundamental trust in scientists and other bodies like government. So it's very easy for these projects to go wrong if it's seen that we're not somehow helping people improve their lives, which is tricky because research by its nature often does go wrong. So there's a kind of gap that needs to be bridged between people's expectations and what science can actually offer. Okay, so now we're going to take a step into the next section, which is we're going to take a leap into technology, and we're going to see what technology can offer earth science. So here are 4 instances in which sensors which I have constructed have been deployed at various locations to monitor river level. This is a river level sensor being put on a bridge in Nepal. Groundwater level. This is a groundwater one in Somalia. To get the relevant permissions to fly out to Somalia was so difficult that it went all the way up to the Vice Chancellor of Imperial College, which is where I was at. It took about 6 months to get the permissions to go to Somalia. Very interesting country, but very limited groundwater. So we were monitoring groundwater here. Tanzania, here's a bridge, we are monitoring river level. And over here, we are monitoring landslide displacement. This is a big dam, a landslide in Nepal. And eventually, you will get a big dam forming behind the landslide, and then it'll burst, which is one of the major hazards in the region, outburst dams. So in each of these cases, I have installed sensors, which I built myself, in order to monitor things like river level, groundwater, and displacement. So let's take a step back first of all and say, why are we using these kind of low cost, off the shelf sensors in earth science? What do they offer us? So the fact is they are very cheap. You can, if you have the relevant electronics experience, you can do it for maybe under £100, things like monitoring a variety of different observables like ground displacement from earthquakes, emissions from volcanoes, water level, water quality. And many of these sensors can easily be fitted onto a smartphone. And there are indeed lots of sensors intrinsically within a smartphone, like accelerometers, which can be used with a little bit of technological expertise to measure all sorts of interesting geological things. It fits into the narrative of open science. We're all for democratization of science. It's breaking down the ivory towers in which we conduct our research. And it is very flexible. So this is a rain gauge and this is a river level sensor. So it fits with the kind of principles of citizen science extremely well, in that everybody in every developing country that I've visited, even though there may not be water or mains electricity, everybody has a smartphone, often far more sophisticated than my slightly obsolete model here. So people have smartphones, people use apps, they're technologically literate, and so it follows that they may be interested in doing data collection, which from a scientific point of view makes my life a lot easier if I have data time series which are spatially dense and temporally dense. And that's one of the major benefits of citizen science projects from a scientific point of view is data. You get loads of data. Of course, data quality is another issue which I won't go into, but that's one of the things which needs to be further investigated using data from non-scientists. Okay, it's a bit of further background. So a variety of different things can be built or constructed using off-the-shelf sensors and open source hardware like Raspberry Pis you may have seen. Some of your children, relatives, grandchildren may have used Raspberry Pi, tiny little computers. So this young chap constructed some sort of an automatic earthquake alarm just using an off-the-shelf Arduino board, which is like a Raspberry Pi. And he got into the papers about doing this because this rivaled the very best earthquake early warning systems, and he did it for about $100. Similarly, down here, this is a younger version of me in Tanzania demonstrating a sensor which monitors the levels of a water butt as a means of kind of improving irrigation strategies for local farmers. So there's all sorts of different areas beyond water which can be addressed using these new technologies. Okay, but I would like to focus just for the next 5 minutes or so on 3 very specific sensors which are dear to my heart, which are more hydrology than earth science, but you know, there's lots of overlap. So When I was a postdoc at Imperial College about 5 or 6 years ago, I developed a new kind of sensor which monitored river levels. So this was based on the principle that near-infrared LiDAR radiation, so a laser, an infrared laser effectively, is actually scattered extremely well by water. So the water surface acts as a very rough surface to laser radiation. And so what you can do is if you fire a laser at the water and measure the time the pulse takes to be received, you know what the speed of light is, so you can get a distance very, very easily. And the great advantage is these laser units are actually relatively cheap and they can be hooked up by some very dodgy electronics here. This is my own handiwork. To data loggers, to telemetric systems, so the data can be sent globally, if you like. And it's very easy to change what this sensor is doing on the fly. You don't need a huge amount of programming experience. You can easily tell it to record 10 times a second or once a day. Very easy to do. So this is me in the hands of a few of my MSc students building these sensors. And we deploy them in lots of different places. So we spent a long time on the banks of the River Thames in Battersea, just on the other side of Battersea Park, where we did a kind of proof of concept study to see whether we could measure the rising and falling limbs of the Thames according to the tides. So this is what we did. So x-axis you've got time, and on the y-axis you have distance to the water. So you've got to imagine these graphs flipped, because if the distance to the water is less, then the water level is actually going to be higher, and vice versa. So what we're seeing here is one complete wavelength, I suppose, of a tidal cycle of the River Thames. Now, interestingly, you may have noticed on this graph up here at the top, I've got all of these different degree signs up here. So what this is indicating is another advantage of the LiDAR system, which is it can be inclined at various angles to the water surface, and you still record the data. The signal would still come back, unlike many other techniques. So what this means is the sensor can be placed on a river bank. You don't need a bridge. You don't need to be firing directly down onto the river, and you can kind of capture the river level from a very, very oblique angle. So some initial tests on the River Thames. We then did this in practice using local community members on a region of Nepal that we were interested in. This is the region which NERC gave us money to study georesilience, resilience to floods and droughts. So here are two local blacksmiths who built this structure for us and attached one of my sensors to this very long bit of scaffolding over the River Karnali, which is one of the biggest rivers draining western Nepal. And this is the kind of data that we get. So again, we've got time on the x-axis and we've got river level on the y-axis. So two different data sets. We've got the official radar data here in black, and we've got my sensor data in this golden orange dashed line. And you can see they approximate each other very well. The big difference is the government system cost $56,000. My system cost £100,000. So this demonstrates the possibility of the kind of low cost off-the-shelf solution, a technological solution for replicating official data at a much lower cost and in a way that it can be placed in otherwise inaccessible, inhospitable regions where it might otherwise be stolen. So it's a very good way of capturing data very quickly. Okay. Number two, there are three things I want to show you. This is number two. This is again a much younger version of me illustrating a water butt, a smart water butt, which we constructed in the lab. And we've deployed at various places in a trial scheme in North London. So I think there's a community in Uxbridge, there was one in Hendon, there was one in Golders Green, where we gave a load of these smart water butts to some sort of group of target communities, houses, to see how it worked. And it turned out, happily, it worked very well. So what this does, it collects the water, it monitors the water levels coming in, and then depending upon the water levels, it then releases it to select places within the garden. And the user has a little remote control, and they can change the rate of input and the rate of output very easily. So this again uses a microprocessor, and the way in which we devised these experiments was with local people. We had a user group. We had a user group of potential people who might use it, and they told us what they wanted. They wanted to water their gardens regularly when they were away on holiday in summer, and they wanted something to do that required minimal user input. So this is just another piece of technology that was really driven by the needs of our stakeholders, our non-scientists. Okay, the third thing I just want to talk about is rain gauges. So this is a smart rain gauge. Again, there's a data logger which is connected up to an Arduino system, and this measures water levels. This is a tipping bucket rain gauge. So this bucket here tips up and down every time a certain amount of rain is received. It tips, and every tip is 5 milliliters or something like that. So the volumes of rain are sent telemetrically to a base station, where the signal is converted from effectively a text message to a wireless signal, which is then fed back to us in Britain. So we installed loads and loads and loads of these rain gauges with local farmers and local blacksmiths who built these stands down here. And we use these to address a hydrometeorological problem, which is making satellite estimates of rainfall better. So at present, in many places across the world where you don't have rain gauges, we have to rely on satellite estimates of rainfall, which are based on radar estimates of cloud thickness. But these tend to be quite bad, and they're bad in terms of error and precision, and they have a very, very big footprint. So this is what the satellite data actually looks like in the raw format, these weird ellipses. If you see these all line up like this, like that, and these correspond to satellite swaths. So satellite is tracking along tracks of the Earth, and they take these footprints, these snapshots of select areas, and this is colored by rainfall, effectively. So what this misses out spatial variability, temporal variability, and it assigns one value to a very large area. So what we did with our community installed rain gauges was we developed algorithms to merge the satellite information with the rain gauge information, which are these red X's here, in order to provide a more spatially representative representation of rainfall, which is this square colored in here. So there's a kind of convoluted but direct link between involving local people, involving new technologies, and developing new products like this, which will ultimately go towards building better early warning systems and forecasts, which will then come back and help communities by boosting their resilience because they have more predictive capacity to get out of the way when there's heavy rainfalls. So there's a big convoluted circle going on, right from people helping us put rain gauges in the ground and measure data to communities being protected. That's what I hope to get across. Okay, this was just illustrating the power of the smartphones in many developing countries. The smartphone is king. Okay, so now we've spoken about technology. I'm now going to go into our case study, which is in Nepal, where we were interested in boosting resilience to landslides and floods in the region of Western Nepal. And we did what is known as, in social science circles, as staging an intervention. This is what social scientists say when you have a particular case study, when you put a lot of effort into nurturing a target community, trying to tell them that we're scientists, we're about to come in, we would like to identify your problems, we want to help you, but also develop good scientific outcomes. So in social science speak, this is known as staging an intervention, which is exactly what we did in Western Nepal over the period of 2 years. So effectively what we were doing in a very simple way is we went into a secondary school and we did a quid pro quo. We gave free lessons. We gave lessons in earth science, landslides, hydrometeorology, and hazards. So we supplemented their curriculum in exchange for the pupils' help in data collection. So the pupils were all equipped with, we call them rain gauges, you might call them measuring cylinders. So we bought lots of these and we gave each pupil a measuring cylinder. They recorded the rainfall each day at their house. And so in that sense, we had a super high resolution data set of precipitation, which could then be compared to our rain gauge on the school roof, which could then be compared to the rather terrible satellite estimate of precipitation. So this is the class. Of course, Nepal's strongly segregated by gender. So these are the boys. You see the girls, of course, sitting behind the boys. And this is us. So we had our local facilitators who took over and I kind of took something of a back seat. So this was really, we tried to be very careful. We twinned with social scientists to try and understand what the schools wanted, what the organisational capacity was like, and whether this could be sustained beyond when our NERC money ran out. So the very worst thing is if we go in, fill these students' ideas with heads with loads of ideas, promise things that we can't deliver, then our funding runs out and they never see us again. So trying to embed local sustainability and ensure this was carried forwards by the school teachers was very important to us. And this was accomplished by developing various infographics about landslides, about the geology on which they are mostly formed, these kind of very friable schists, about the monsoon and about the water cycle. And much of our material was translated into Nepali. Okay, yes, we have many objectives as well. So this is the data. So what you're seeing here, the grey background is our rain gauge. This is 1 year. You see the monsoon is here. And then this is precipitation on the y-axis. So rain gauge on the school roof in grey, the satellite estimate in the black dotted line, and an average of all of the students' data in this red line. And what you can see, isn't it quite amazing how the students' data, and these were 14 and 15-year-olds, tracks the rain gauge incredibly faithfully, very well in magnitude and in time. And then if you compare it to what the satellite is doing, it's all over the place. It's missing these extremes up here, it's not capturing them. And then the satellite is doing some weird stuff over here, saying there's rainfall where there isn't rainfall. So this is because the satellite data is subject to smoothing algorithms over several pixels, which is kind of 10 kilometers, 20 kilometers. So this really demonstrated to us the value of employing a citizen science approach, even with young kids, in yielding a data set which was accurate, precise in space and in time. So we saw great value in that, and we published on that a few years ago. There are other methods which we can use. It's not all about data collection. We also work with local people to develop their knowledge of the local area by mapping landslide hazards. OSM is OpenStreetMap, which is a freely available app which can easily be downloaded onto a smartphone. So basically, we work with local people to say, where's the hazard? What do you know about it? Can we apply any of your knowledge, your indigenous knowledge, into our models? So for instance, we found out several useful nuggets of information about spring lines which had been hidden. We didn't know about these springs. And then from that, we worked out there was a change in permeability in the strata. And then we could say a lot more about where we wanted to position our geophysical surveys. So incorporating local knowledge is super important to make sure that one is not reinventing the wheel in these surveys. Yes, stakeholder mapping and having many meetings with the stakeholders, very important. In many countries that I've gone to across the global south, these meetings tend to be very elaborate. They tend to take a whole afternoon. You will spend maybe an hour doing introductions, and then you'll have a very big meal with lots of water, and the head of the local farmers cooperative will get up and do a speech, the head of the police will do a speech, the head of the army will do a speech, and then we have about 5 minutes at the end to rapidly demonstrate what we want to do. So this is a box that must be ticked when you're doing these things. It's fundamentally pointless, but it greases the wheels. And a lot of the work that I do is about greasing the wheels. This is something which has to be done. Okay, other techniques where the input of local people is super important is landslide mapping. So this is related to risk mapping, but this is more directly linked to the kind of geological, geomorphological phenomena behind landslides, like lithology, slope, land use, that kind of thing. And ultimately, members of the local community are fascinated by our geophysical kit, and they love to help us out actually doing the surveys. And when I say help us out, one has to be careful not kind of pushing the tasks onto local people of moving the survey line along, carrying the box, all that kind of stuff. They have to be equal partners as much as possible. So we offer the data to them immediately afterwards, which they're very keen on, even though the electrical resistivity survey results are of limited use to a very small rural community in Western Nepal, but it fosters a sense of ownership of the data. Okay, so let's step back from Nepal and let's take a whistle-stop tour through 3 slightly disparate places. I apologise if this seems like a bit of a mix and gather bag, but I feel like these are the 3 other locations in which I've used citizen science approaches with a degree of success. So let's start off with the farthest flung region, Madagascar, which is very beautiful, has relatively little in common with Nepal geologically or tectonically. Has a lot in common with India, because it rifted from India far more recently than it rifted from Africa. So Madagascar and India are conjugates. Anyway, what you can see here is much of Madagascar is an extremely flat plateau. If you know your geomorphology, it was here that Lester King, the great South African geomorphologist, first developed the theory of penny plains. So the idea that these flat surfaces come in response to periodic bursts of uplift, which our group, this was when I was a PhD student, related those discrete pulses of uplift to a mantle plume, which sits underneath Madagascar. Anyway, we're not so interested in the geodynamics as the surface expression of this uplift, which forms these beautiful erosional scours, revealing these thick piles of laterite. These have the local name Larvica, which is the Malagasy term for little hole. And all of central Madagascar looks like this, big flat central plateau with these deep erosional scars revealing bright red laterite. So this is a map of Madagascar coloured by rates of surface uplift. Red is highest uplift, centre of the island, which is coincident with recent volcanism, which are these red blobs. The black dashed line is the region within which you get the most of these erosional scours, the highest density of these larvica. So what we're interested in is correlating this map, how fast the surface is going up, with the thickness of laterite, because we know that where the laterite is thicker, farmers can't grow anything, and these regions tend to be poorer. So what we did was, with our partners in the capital, Antananarivo, which is there, we developed a citizen science network of local people with some degree of geological competence who would go out, do corings, and measure the thickness of laterite in their immediate locality. So this is what the laterite succession looks like. You have a very hard iron-rich layer at the top, laterite, saprolite, and then the bedrock. So we had a network of people throughout the country measuring the thickness of this layer at the locations indicated on this map by the little circles here. So from this data, which was collected from our non-scientist network, we were able to produce a map of thickness of laterite. And there are 2 patches where this pile of laterite is incredibly thick, south and in the north. So in other words, in regions bounding the very, very high uplift region in the center. So this was very interesting, and we thought that what would it look like in a kind of wacky, maybe not entirely scientifically sound way, if we took this map of laterite and compared it to a map of socioeconomic poverty across the island. So this is what we did, and this is what the poverty map looks like. Oh my goodness, look at this. It's almost too good to be true. So I wrote a paper about this, and I very boldly stated, laterite causes poverty. And the editor returned it to me, essentially saying, try again. You are being too overconfident. So we changed our argument slightly, and we argued that you need the rates of surface uplift, where they're kind of moderate, that governs the formation of laterite, and so therefore surface uplift, which is governed by a mantle plume, may tell you something about how much poverty there is going to be via how much agricultural productivity there is going to be. So I think we worded it in a slightly mealy-mouthed way, something like rates of surface uplift are modulated modulate agricultural activity, which may have an effect on levels of poverty. So we kind of did a very wishy-washy explanation of it. But the long and short of it, and the relevance to this talk, is it's just illustrating the power of engaging local people who are interested in your work. They're interested in working out potential maps of where agriculture may or may not take place. And the government of Madagascar is quite interested in this as well. So engaging local people with research which is interesting and relevant to them while also being scientifically useful for me so that I can write a paper is one kind of name of the game of this citizen science thing. Okay, so let's take a leap out of the global south and now enter the global north, specifically the Cotswolds, which is where I grew up, which is a lovely part of the world. And I chose it in this order because the Cotswolds actually geomorphologically bear more than a passing resemblance to Madagascar, incredibly. Look at this. The Cotswold Hills are a misnomer. They're not really hills, they're a plateau. Top of the Cotswolds is like a billiard table, completely flat. This is the western edge of the Cotswolds. This is a town called Stroud, which is halfway between Gloucester and Bristol. And the western flank of the Cotswolds, which is here, is incredibly steep. You may not appreciate it from this photo, which is taken a long way away. But this is the Cotswold Scarp, which is very steep. It looks like that. And we're interested in this region over here, the region next to the River Severn. So why have we gone to the Cotswolds? Well, first of all, let's have a look at a couple more maps. I'm interested in this part of the Cotswolds. This is Stroud, Cirencester, Gloucester, and Bristol is somewhere down there. So this map is showing slope, and so what you can see is at the edge of the Cotswolds, the western edge, you have these incredibly incised valleys, very, very strongly incised valleys. I could stand here and stare at this map of slope for half an hour. It's so beautiful. You can see the River Thames, the headwaters of the Thames up here. This is Kemble down here somewhere. And you can see the fault action. Do you see that? Doing something like that. And indeed, the faults are up here on the lithology map. So what this has done, this dramatic river incision, where there's a river which pierces the Cotswold escarpment, like this river here, the River Froome, it cuts through the stratigraphy which is like a sandwich of permeable, impermeable, lias, limestone, Fuller's earth, limestone. So because you've got this permeability sandwich, you have springs. So the river incision has carved out, just like an ice cream scoop, through the stratigraphy, revealing the highest spatial concentration of springs, these yellow dots, in the UK. So there's lots of very, very powerful and productive springs, which incidentally allowed Stroud to become one of the textile capitals of the UK. And the bays for snooker tables, the green bays, is still made in Stroud, as is the red of the tunics of kind of dress uniform for British soldiers. So it's all made here because of the steep gradients of these kind of valleys here. Anyway, I digress. So why are we interested? This is an entirely different aspect of science compared to Madagascar, where we were interested in kind of pedogenesis and soils. We're interested here in groundwater and springs. So using the same techniques, we established a network here in Stroud, and we got lots of retired people this time, very interested in monitoring spring fluxes, how much spring volumetric flow rates change throughout the year. So we all gave them little bottles and a little timer, and they monitored discharge at various springs throughout the year. And also the position, because the springs migrate up and down depending upon the time of year. So we were interested in elevation and flow throughout the year. And we had about 170 respondents measuring discharge from 170 springs across the mid-Cotswolds. So this is kind of what I meant by springs migrating up and down. On the left-hand side, we've got some beautiful high-resolution LiDAR imagery of a valley with some rivers in it. And you can see the blue dots are the kind of lower or summer positions of the spring. And the light blue dots up there are the higher, the kind of maximum, the winter levels of the spring. And because you're dealing with this very porous succession of oolites, and this is the Cotswold sand, now called the Bridport sand. The level of the water table marches quite merrily up and down, so that manifests at the surface as these springs moving up or down. And in the summer, where you have a dry valley, these are known locally as winter boils. Okay, so we did this, and we established some fairly clear relationships between discharge and elevation change. So the bigger springs didn't tend to move around much, and the smaller springs tended to jump up and down and move their position all over the place. So what we were interested in doing, actually here, the next slide, is thinking about how we could bring in geophysics to this. I'm a geophysicist after all, and think about taking a slight leap of faith here, a major archaeological problem. So one of my best friends is an archaeologist, and he was very interested in the fact that he thought that springs were right next door to various archaeological phenomena like long barrows when they were constructed in Neolithic times. Now, nowadays, they're generally nowhere near each other. So this picture up here, if we focus on the close-up, these blue dots are springs coloured by discharge, and these white features are various archaeological phenomena. So the triangles, for instance, are long barrows. So we developed a really broad brushstroke inverse model using geophysical inverse theory, which used the present-day relationship between discharge and spring elevation and extrapolated it way back into geological time, or rather human time, back into the Neolithic. So we were wanting to ask the question, can kind of human scale changes in spring elevation and discharge be replicated back into the distant past, into the Neolithic, to suggest where these springs might have been in Neolithic time and what their discharges might have been. So we formulated this rather complicated problem, and we got a lot of flack from hydrogeologists because there are various things that you can't really do, which we did. Made huge assumptions about the oolite aquifer. It's actually a lot more complicated than we made it out to be, but we stressed that we're approaching this problem with our geophysicist hats on. We're not hydrogeologists in this particular piece of research. So we ran our model, and can you see that this is the present day, this is Neolithic time. The position, the springs are essentially far closer to the monuments, the Neolithic long barrows, in almost all cases, using a very simple model for all of the Cotswolds. And the discharges are generally greater. So if we look at this box here, where this spring has suddenly migrated far closer to the long barrow here, I'll show you a picture of what that looks like. So we think that the spring that is currently down here, and there's a dry valley here, in Neolithic times, it was right next door to this long barrow up here. I would go into more detail, but I may not have the time to explain the model. It's all there in the paper, should you wish to read more about it. But fundamentally, again, this was predicated on getting huge volumes of data, data pertaining to spring discharge, spring elevation, from local people, from retired people who wanted to see something like this, who took an interest in their surroundings. And generally in countries like the UK and the US, the people who you engage in projects like this are either students or retired people, just because they don't have time on their hands. So that was the Cotswolds. Now I wanted to wrap up and finish with, on a high note, by focusing on the most closely linked topic to the Thames Valley Regional Group as I could muster. So this is our work on the water resources of the southeastern London. So this is a graph which I show to all of my hydrogeologists and to my master's students and to my first years verbatim. This is groundwater level under central London over the past 170 years. And it's a lovely graph which illustrates overzealous abstraction, dewatering the London clay until they realised there was a problem in the 50s. There was various water abstraction acts which put strict limits on unlicensed abstraction. As a result, you had slow recharge through the chalk, again through the Lambeth group, which caused problems, caused foundering of buildings, it caused differential movement of the London Underground. So Tony Blair instituted this strategy, the Guarded strategy, which has stabilised groundwater levels at the moment about the base of the London clay. This is Trafalgar Square under central London. So this is just to illustrate the groundwater level has jumped around quite a lot. We will get to the citizen science aspect in a minute. These are the fountains at Trafalgar Square. It used to be artesian, no longer artesian for a long time. These are now fed from the mains. So this is a slide which I really should update. This is predictions of the supply-demand deficit for South East England in 2013. Now, I really should get the most up-to-date versions, but I like this because it illustrates that back then, you see this big red region, which is a yawning supply-demand deficit, which persists to this day. There are much of South East England that is more water stressed than places like Rome, like Houston in Texas, or like many places in Israel. So it's a real underreported issue, in my view, water stress in South East England. So what's happening about this? Various strategies have been employed. This is perhaps one of the most environmentally deleterious, is the desalination plant at Barking, which was installed, began operation 13 years ago. So the idea is Thames water is taken in, reverse osmosis is used, which gets rid of the nitrates, the salts, the bacteria, etc., and yields potable water for human consumption. Now this was deemed okay back then, but now as the energy transition is drawn into sharp focus, this is seen as a bad thing. And as our energy bills are going up, this uses huge volumes of energy, and so other solutions are increasingly sought. One solution, this is where I come in, or at least my research. One solution involves the use of rocks as a kind of natural filtration system by which you can put grey water into a column of rock, and all of the, or many of the contaminants, viruses, bacteria, heavy metals, will be, if not eliminated, at least arrested and absorb onto the surface of the chalk. So this is an idea that isn't particularly new. It was floating around in 1924, where the standard uses beautiful words describing the use of chalk to transform dirty water into soft water suitable for man and beast, and indeed the chalk aquifer being sufficiently capacious for this use. Recently, it was picked up by The Guardian in a piece which was discussing similar schemes across the world. So we thought what we would do is we would have a look at chalk section. Of course, transmissivity in the chalk is dominated by the fractures. So we wanted to model fluid flow through the chalk by first simulating what would happen using an exemplar outcrop. This is Dumpton Gap near Ramsgate in Kent. So we took a picture, just to illustrate how meaty the chert bands are at this point. I think this is the Seaford chalk, maybe? I'm not sure exactly. Took a picture, which we then digitized, a very simple way, by picking out the fracture sets, measuring the apertures and using a very simple law to assign permeabilities, and then drawing these fracture sets in a computer-aided drawing program, and then putting a mesh over it so that we can run a model. So this is great, but it was hugely time-consuming, and this whole process took me about 2 months. So this is where enter citizen science like this to make my job significantly easier. So again, we followed the same process. We convened various stakeholder workshops and community groups. And this time what we were engaging non-scientists to do was to do this, to take pictures, to monitor the thickness of fractures or the aperture of fractures, and to, for the more geologically literate stakeholders, to estimate what the attitude of the fracture sets might be. Now, a key lesson from this work is not to underestimate the scientific capacity of the general public, which might perhaps surprise you, but I was pleasantly surprised by how many people knew how to use a compass clinometer without much instruction from me. So they were able to measure dips, dip directions very easily, so we could get a rough handle on what the fractures were doing at many locations across the southeast. So the purpose behind this is once we have our digital model of the outcrop, these pink lines are meant to be the fractures, we can simulate a water flood across it. So what I'm doing here is I'm forcing wastewater or grey water from the left-hand side to the right-hand side under a pressure gradient of, what is that, 400,000 pascals, 0.4 megapascals, just to see how fluid would flow through the chalk. So obviously it's guided by the fractures. That is how fluid flow goes through the chalk. But then, if you let the model run, you have release at the right-hand side after about 7 weeks. But interestingly, you have this effect over here. This is diffusion. Now, where the water imbibes from the fractures into the matrix and vice versa, this is where you get your essential cleaning reactions, which are very exciting to the process of improving the quality of the wastewater, which I'm interested in. So what our citizen science observations enable us to do is to do this on a very ground scale and to ask the question, what do the fractures do throughout the syncline? Are the fractures the same in their disposition at Ramsgate as they might be in the North Downs, as they might be in Tring, in the Chilterns, or somewhere like Devil's Dyke in the South Downs? We have lots and lots of fracture measurements, which I need to do something about. Okay, so finally, this is kind of taking one foot out of citizen science and just presenting another place that we want to go with all of our fracture data. We want to develop a discrete fracture network underneath London because I have a PhD student working with TfL on addressing the question of how do we cool down stations of the London Underground. It's incredible. There's been very little research on this. TfL seem to rely on big fans in the middle of stations, which just move hot air around. And so our thesis is we could place heat exchangers within the stations. This has been done at one station already in Victoria, but it wasn't very successful and TfL ran out of money. In order to take groundwater or water from various subterranean rivers, which have now been blanketed by concrete, and effect a heat exchange process. Hot air runs over cool water, resulting in cold air and warm water, which is then discharged to the sewerage system. So we are very, very interested a priori in understanding what pumping from the aquifer would do. And so in order to work out groundwater flow patterns, we need a discrete fracture network, which is where all of our observations from the non-scientists will be exceptionally useful. And this is just a schematic of a typical heat exchanger. So we've done some preliminary work and we're just in the middle of, we've got a load of cores from the Thames Tideway project. And they're going to come to Holloway on Monday. And we're going to analyse them for fractures and for the quality of the chalk. One thing we have done is we've looked at groundwater level, and these are the position of the kind of lost rivers underneath London. The colour in the background is groundwater level. It's obviously deepest underneath central London. And we plotted the various tube stations here. So obviously this is the Northern Line, Bakerloo Line, these are all the lines. And we coloured each station red, you see a little red outline here, or blue, little blue outline here, depending upon whether we thought using river water or groundwater would be more environmentally sustainable and more economically viable. So the blue ones are, like South Kensington here, are where we suggest the use of groundwater is better. And the red outline stations here are where we suggest using river water would be better. I won't go into detail about our selection criteria, but if you want to know more, there is a paper on this that we published last year. So that was slightly tangential to finish off, but that's just illustrating one of the things that can be spun off using citizen or non-scientist observations. So I will close there. I've left all of the papers which I've mentioned. So going all the way from an overview of citizen science to the water level sensor that I mentioned, to our intervention, all the way down to cooling the London Underground and using chalk as a filter. Thank you.
Beat me to saying that's Jonathan for his talk. It's really good. I think that was really insightful in terms of how you can use different communities to gather data with scientific research, which is incredible. Are there any questions from the room first, Jonathan? And if there's anyone's got a question on Zoom, feel free to put it in the chat.
I normally do this on the seminar coordinator for the department, so I know the questions and arrow to your heart.
I always take it as you've just done a very good job.
Well, that's the optimistic approach.
I mean, I had one which was just sort of in terms of some of the drivers for citizen science approaches, whether it's more the researchers' aspirations that are driving it, or whether it's more issues being risen upwards from the citizens itself, which are the big drivers. I was wondering which plays the strongest.
That's a good question. It's a complicated question to answer.
That's why I asked it.
Yeah, I mean, a bit of both, really. So there's a fine line between kind of being a charity and researchers, and this is the closest you can get to kind of feeling the impact of your research. And I like that. I like going into communities, working with people. It's nice to kind of research in action and seeing actually people's lives improved in front of you. But having said that, we should be realistic about this and know that citizen science approaches are useful because they combine with technology very, very well, which is good for a lot of funding applications. And also they tick a lot of UN Sustainable Development Goal boxes. So there's a kind of practical and there's a kind of idealistic reason for doing this. And I think, there are many disciplines where it could be expanded. Started off in biology, people counting Christmas turkeys in America each year, the Audubon Society. And it's only really come into Earth science in the last 5 years or so.
Excellent. Any questions from the room? I've had a bit of time to think. There's one.
Bit of a general question, but just if any of us or just anyone in general was interested in being involved in citizen science, are there sort of networks or larger organisations that exist to sort of try and direct people to what's going on in their area or research that may impact their communities or that kind of thing?
Not that I'm aware of. So there's no kind of overarching UK citizen science thing. Mostly, most of the work that's taking place now takes place through funded research, so funded by the research councils typically. And if you do want to get involved, it's probably worth doing a Google search for either citizen science or kind of participatory monitoring in my area, because at the moment I think it lends itself more to water science and geohazards more than kind of science writ large. You could ask people to identify fossils on the beach or something, but to what end, what research end does that really serve? But it's really useful at the minute for people who are interested in water quality and quantity. You've heard a lot about the volumes of sewage being released at the seaside. So there are various schemes involved. People taking photos, simple as that, taking photos and uploading them to Twitter, which is then kind of the information is harvested, and then things can be drawn from that. So there's a lot of stuff on social media that would be a place to start. Mostly old social media, like Facebook. But yeah, that would be a useful place to start too.
Thank you. Just for the Zoomers, has anybody got any questions? Anything in the chat or typing? All right, any others in the room? Yes.
Okay, I'm going to go a bit scientific because I'm an analyst in art. How are you confident about the data received from the citizen, and how can you determine
that is the question I wanted to get.
data quality?
That is the question that I wanted to get. That is a question into which
never that before, have you?
No, never.
It's not a plant. That is a question that is the subject of a 450k application to NERC that is currently live, quantifying error and uncertainty in citizen science data, which is one of the biggest problem in my view. Not the sexiest. It's very difficult to dress it up in kind of grant writing trumpetry, but yes, that's a question that is worth several research papers and is worth a large program in my view. There's all sorts of statistical techniques that could be used. What I'm proposing to do is to run a full citizen sciencey observational test of various aspects of the water cycle, groundwater, rainfall, humidity, alongside professional instrumentation, and then cross-compare the results and see what happens. And then to ask questions like, does the inclusion of local knowledge into a model, can that be done, and does it improve the model? Because the big problem is, you have people who spend their lives learning about various earth science and geological, hydrological aspects. wouldn't it be a shame if that didn't give us some advantage when we're doing data collection? Yeah, there are many instruments which are very hard to read or hard to calibrate. So there are some things which just can't be done using non-scientists, and you do need a kind of guiding hand going along. But yeah, that is, in my view, the key thing to do with citizen science, which must be addressed.
Johnny,
Chat as well. Get to that.
I get the feeling that you're implying that the data quality produced in citizen science may not be the highest.
It's variable. I mean, you saw
It's variable.
the rainfall data from the pool was actually excellent.
Well, yeah,
These were
superb data.
these were children, but the problem is it comes down to motivation. If people are bored, they'll give up halfway, so you'll get a data set that's got a gap in it, which
Yeah.
has to be smoothed over or something, or they'll just do a terrible job. It all depends upon motivation, and students and retired people tend to be the best. It's
Yeah.
working people who don't have time, who
What I was going to ask is that in those initial sort of discussions that you have to get them involved and encouraged to carry out the citizen science, the actual measurements, is there an element of training involved in that?
Yes, yeah, that's a good. These questions are excellent. They're highlighting points which I've forgotten to say. I did show a slide of a kind of stakeholder training workshop, the one where they had the big meal beforehand. There was a serious point behind that, that often these workshops take place over 3 or 4 days, and there is training in kind of basic methods of the scientific method, things like accuracy, precision, how to read, how not to lie, how to replicate your results, fair tests, all that stuff. So there is training, and mostly people are very interested in having taught from professional scientists, which people like that, you know, coming into it. Doesn't often happen to many communities where they have training or education or something. So knowledge transfer is, I suppose, the au fait word for it, isn't it?
One last question, this one from the Zoom.
Aha,
As
we have listeners.
So this one's from Carol. Do you think water companies, etc., could get useful citizen science data to tap water quality of potholes? How could citizens keep trust in who they send info to?
That is another excellent question. The question of IP trust, anonymization of answers. This is another thing which often comes up. Yeah, that's a really tricky one, because I think trust in water companies, particularly water bills, is at an all-time low. Yeah, so potholes and tap water quality. I think if the people who are doing the measurements are sufficiently convinced and they have buy-in to what they're doing, that somehow it's going to make things better, then, you know, there'll be more trust in the project and they'll do the measurements and it'll be more sustainable. But if they're just kind of if they just think that it's a way by which Thames Water can just get more data or just do it on the cheap, then they won't be interested. I mean, I think it's tap water quality is very interesting in tap water taste hardness. The question is, doing the actual analysis is maybe a bit tricky. But potholes certainly it's better than writing a letter to the council if you can actually compile a database. And then the sense of doing that is it brings you a sense of agency, that I am part of the solution. You know, if there's a paper, you have your name on it. So that's another important thing about citizen science, this sense of agency and empowering people, which traditional data collection methods often don't do.
I'll draw it to a close, but with a quick prompt on our next meeting will be, which is on the 12th of April, and this will be held at the Food offices in Wallingford. We've got Warwick Mortimer.
Yeah,
Going to talk
Captain
about
Chalk.
counting fracture logging in the chalk. So
Oh.
expect to see you there.
When is it? I'm going to be doing that on Monday. When is that?
It's 12th of April, Wednesday.
Well, can you send me an invite?
I will.
Come along and tell him what I've been doing.
So yeah, so I hope you can all join us. I think we're still looking into whether it can be hybrid or whether it will be in person only. So that's.
I appreciate that.
Yeah. So I'm going to close the Zoom meeting now, and then who is left in the room? We have some refreshments.
Lovely.
Sandwiches and some grub. So thank you everyone for on the Zoom, and we'll see you soon.
Thank you.
Bye.
Bye.
Fine.